In the previous lecture, we discussed the calculation of the work done by a particular force, perhaps just one of many forces that may be acting on an object that moves while the force is acting. I showed how we can use the average value of the force to calculate the work done, provided that we're told what the average force is, which is rarely the case, or we can see or are told that the force varies linearly in a straight line or regular fashion. An alternative way to calculate the work done is to agree that it's true that the work done by a force equals the area that is below the force versus distance curve, the area between that curve and the x-axis. Let me show you what that area is for that previous force, the graph of which is reproduced here. The area in question is swept through by my hand here. Whatever that area is, measured not in the kind of units that you're accustomed to, which is square feet or square meters or even square miles, but an area measured in different dimensions, Newton meters, Newton times meters, which we found last time, or were told last time, is the unit known as a joule. Let's calculate the area under that same curve and find that it's the same number that we found before in the previous lecture, which was 9 Newton meters, same as 9 joules. Well, the area under this portion of the curve here can be imagined to be the area of this triangle plus the area of this rectangle. The area of this triangle is 1/2 the base, which is of length 2, times the height, which goes from 1 to 2. Well, that's just a 1. Final result there is 1, and the units are work units, which are joules. Now the area of the rectangle is width times height, which is 2 times a 1, or 2 more joules. Then we've got the area under this portion of the curve, which is the sum of these two areas. The area of that triangle, I'll put it up here, which is 1/2 the base, which is of length or width 2, times the height, which is 2, for a total of 2 joules. And finally, you've got the area of that rectangle, whose width is 2 and height is 2. It's this area there. And that works out to a rectangular width of 2 times the height of 2 for a total of 4 joules. Now, this works out to 4 plus 2 is 6, plus 3 is 9 joules. I misspoke a couple of minutes ago when I reminded you that the work we found previously was 6 joules. I believe I said that. Apologize. The actual answer then, as now, is 9 joules. In cases where the force doesn't vary linearly, as it does in this graph, where areas are comparatively easy to discover, there is a different, more cumbersome brute force method of finding the area under a curve that looks, well, perhaps like this one, where force is again plotted versus F, and you might have a curve such as this. The area under all of this curve shown here can be approximated by a method known as counting the squares, the grid squares that appear on a sheet of graph paper. Count the number of grid squares that appear or are found under the curve shown here. I'll leave it for you to check the example problem that's worked in the notes for chapter 6, part 1.